Right. Welcome to Math 150, Section 2, Lecture 20, 2021. What we're going to be doing today is we're going to be talking about sequences and series after we just do a little bit of a multivariable calculus review. There was a request to talk a little bit more about interchanging orders of integration. So I'm going to just do one of the examples. It's interesting at what moment the screen decides to resize itself. It's always a variable time of the class. And then the test, I will email directions on everybody on what it is. For those of you who are in class, you have copies in front of you right now. Right. So we have two curves, y equals x and y equals x squared minus 2x. And we want to find the area between them. There's a lot of ways to find the area between them. One is you can do it as a one-dimensional integral by integrating the height of each value, or you can do it as a two-dimensional integral and integrate the function 1 over the region. Either way is fine. So the first thing you should always do in a problem like this is draw it. The line y equals x is not that bad to draw. It's just a straight line like this. For y equals x squared minus 2x, it's nice to think, where might this line, where might this parabola be 0? So can you look at x squared minus 2x and quickly see where this is going to be 0?
0 and 2.
0 and 2. So in fact, this is just x times x minus 2. So here's 0, here's 2, and in fact, we know that the vertex of a parabola is halfway between the roots. How would we find where the parabola hits the line? How do we find where the parabola hits the line? Set them equal. So if x equals x squared minus 2x, then 3x equals x squared. So x squared minus 3x equals 0. So we really put the answer. X times x minus 3 is 0. X is 0 or 3. Oh, good. We already have one of these points. And here's the second one. This is both a horizontally simple and a vertically simple region. Great. The question becomes, would you rather do the vertical integrals first and then the horizontal, or the horizontal integrals and then the vertical? Do you have a preference? Well, if I do the vertical integrals first, I'm always going from the parabola to the line. If I do the horizontal first, over here, I'm going from the line to the parabola, but down here, I'm going from the parabola to the parabola. I would have to break this up into two different regions. It's not a huge deal. We'll do it. We'll see it's not that bad. But for this problem, it is more natural to do it vertical first. So I need to fix an x. So what's the range for x? When you look at this, what is my range for x? 0 to 3. And now I have to figure out what is my range for y. And so for the range for y, I go from the bottom to the top. So I want, you can either do y bottom of x, or you could use L of x for the lower. Well, it's going to be really easy to figure out what that is because I give it to you as y as a function of x. So what would the bottom curve be in this example? Yeah, it's just x squared minus 2x. Here's my bottom curve. And if I want the top, y top of x, or u of x, up of x, it's just going to be this line over here. The line is y equals x, so the upper is just going to be x. And so we get y goes from x squared minus 2x to x of 1 dy dx. Right? So the first thing is I do the y integration. So what function as a function of y has derivative 1? What function has derivative 1? Y. So it would just be y evaluated x squared minus 2x as the lower bound, x as the upper bound, dx. So this is just the integral x goes from 0 to 3 of x minus x squared minus 2x dx, right? Is this right? What's the... Yeah, I dropped the minus sign. I'm supposed to subtract off all of x squared minus 2x. And so I don't put in the parentheses, I didn't distribute the minus sign. And to be even more pedantic, I'll put square brackets here so that the whole thing is being divided by dx. So this is the same as the integral x goes from 0 to 3 of 3x minus x squared dx. So this becomes 3x squared over 2 at 0 and 3 minus x cubed over 3 at 0 and 3. And then when I plug in x equals 3, I'll get 27 halves minus 27 thirds. I'm not going to simplify the 27 thirds because this way the two numerators are both 27. So 27 halves minus 27 thirds is 27 sixths, which is the same as 9 halves. You can check and see if this answer is reasonable by saying, well, if I just draw a triangle like this, what's the height of this triangle? When x equals 3, how high do we go up for y? 3. And so, this kind of looks like the same area as the cap down here. And if I just tried to estimate this by the area of the triangle, base is 3, height is 3, that's 1/2 base times height would be 9 halves. So it's actually not an unreasonable answer to get 9 halves at the end of the day. Let's see what would happen if we tried to do it the other way. I guess one last thing we can tell is, what's the lowest value of y? What's the y coordinate of divergence? -1, because we know the parabola is x squared minus 2x. The vertex is when x equals 1, so this would be y equals -1. So now, I can actually see from earlier today, roughly where I do the curve. Here's 0, here's -1, here's 3. And I have to break it up into two different regions. And now I have to find the left and the right endpoints. So in this range, y goes from what to what? So in this first one over here, what does y start at? What does y end at? So what's the smallest value of y in this range? -1 at the base of the parabola. What's the highest value of y? 0. And in the other range, y goes from 0 to 3. Now we have to find the x values. So over here, if y equals x on this line, how would you write x as a function of y? That one's not so bad. This is the harder one. Y is x squared minus 2x. I need to write x as a function of y. And unfortunately, it's going to be a different function of x depending on whether or not we're to the left or the right of the vertex. If it is not clear yet that this is the bad way of doing the problem, just wait, it'll become even clearer in a moment, right? So we know y is x squared minus 2x. How can we find x as a function of y? There are two good approaches. How can we find x in terms of y? I'm sorry? Excellent. So how will we complete this rule? What will we add to both sides? We have x squared minus 2x, so to make this a square, what do we add? I'm sorry, not 4, we add 1. So y plus 1 is x squared minus 2x plus 1 is x minus 1 squared. The other thing you could do is you could bring y over to the other side, and you could use the quadratic formula. Both will give the right answer. This allows you to bypass the quadratic formula, and you get x minus 1 is plus or minus the square root of y plus 1, or x equals 1 plus or minus the square root of y plus 1. And so now we know which one is the left and which one is the right. The negative sign, the smaller one, will be the left, and the positive will be the right. So x would go from 1 minus the square root of y plus 1 to 1 plus the square root of y plus 1 dx dy. That's just enough space, the advantage of teaching section 1. And over here, what's the left bound in this top region? X starts off out. So down here we had to use the parabola. Over here, what do we use?
The line.
The line. So what is the left value for x?
Y.
It's just y. And it goes all the way up to the parabola, which would be the plus sign. The 1 plus the square root of y plus 1 dx dy. At this point, it should be clear. This is not the way to do the problem. We've had to split it into regions. We have square roots coming in the integration. As a nice exercise, either do the integration directly or go to Wolfram alpha and see if it gives the same answer. It's nice when you're doing a two-dimensional problem that there's really only two choices. So if one way is not working, pause, put it off to the side, try the other. If that doesn't work, then go back to the original one and see if there's maybe something else that you can do. Okay, any questions about this? So this is exactly how you handle all problems like this. And for these area integrals, there's only two possibilities really for the ordering. If one is not working, try the other. Okay. So it is now time to turn to sequences and series. And so when we do sequences and series, some of it is going to be more like an art form than the math we might be used to. And it's, do you have an intuition, a good way to look at things and see the answer? Well, you've actually seen one situation of this before. If I give you a quadratic, what's your first go-to approach to find the roots of a quadratic? What do you try to do first? Just look at it. So imagine x squared minus 7x plus 12 walks into a math classroom. All right, how would you factor it? What would you think? X minus 4, x minus 3. But there's not that many possibilities. So we need two numbers that multiply to 12. I can write 12 as 1 times 12, as 2 times 6, or as 3 times 4. And because this is positive and this is negative, what do I know about the signs? Both have to be negative. So I know it's either x minus 1, x minus 12, x minus 2, x minus 6, or x minus 3, x minus 4. So there's only three possibilities. As the number gets more complicated, as the numbers get more complicated, you may not be able to just directly factor it, even if there is one that exists, in less time than it would take you to use what? Quadratic formula. When in doubt, you can always go to the quadratic formula and just shove in. If I wanted to be evil and come up with the worst possible quadratic, could I stump you in terms of finding the roots?
You can make them imaginary.
But can I stump you? If I give you any quadratic, can you find the roots? Yes. No matter how hard I try, the quadratic formula will always give you the answer. But it may not give you the answer in the least amount of time. Well, that's okay for a lot of things. I just want to get the answer. If I can do it faster by inspection, I'm happy to do it by inspection. But if not, I have to go to the quadratic formula. For a lot of sequences in series, the first question you always want to ask is, does the series converge? And then if it does, what do you think you want to ask after that? What does it converge to? And then after that, you might even ask, how quickly does it converge? And so for a lot of sequences, we'll very quickly determine that it converges. And a lot of times, the geometric series will be the go-to to prove that something either converges or diverges. So one of the questions is, why do we care about sequences in series? Anybody taking physics here? Okay, so in physics, you often have expansions in terms of either the fine structure constant or Planck's constant. Does anybody know what the fine structure constant is? It's a truly remarkable number. It is a unitless quantity in physics that involves like Planck's constant, the charge on the electron, and a couple of other things, and everything cancels out so that it's unitless. Which is larger, or are they the same, 9.8 or 32? 32 is larger. What if I tell you that the 9.8 is 9.8 meters per second squared, and the 32 is 32 feet per second squared? They're now approximately the same. This is the acceleration due to gravity around the surface of the Earth. The numbers are different, but when you take into account the units, they're the same. What makes the fine structure constant so wonderful is it's unitless. It has meaning independent of whatever units you choose. And a lot of things in physics are an expansion of higher and higher powers of the fine structure constant. And since it's less than 1, the higher and higher powers become smaller and smaller. In quantum mechanics, you often have things that are expanded in terms of Planck's constant. Planck's constant is small. Powers of Planck's constants become damn small, it gets incredibly tiny fast. Classical mechanics is often the limit as Planck's constant goes to 0. You just keep the main term, the constant term, in the expansion. Quantum mechanics then comes into taking all those other things into account. Any people taking economics here? Okay. Have you looked at the multiplier effect for spending? So if I go to a business and spend a lot of money, the business now has more money to spend, and they might have to buy more equipment, more raw products. They will pay maybe more in salaries, and then the people who get that money then spend more. So every dollar that you spend, it's multiplied by a certain factor in terms of the impact it has on the economy. Similarly, when people stop spending, the contraction is multiplied as well. And it's a great example of a geometric series. When looking at the impact of spending, looking at the impact of savings. So there's going to be lots of situations where we will want to understand geometric things. Okay. So just a little bit of notation. So a sequence in terms of A0, A1, A2, A3, AN plus 1, and so on and so on. In section 1, I started my sequence at A1. In section 2, I'm going to start it at 0, just to have a little bit of variety. You can choose where you want to start. And for some things, it's better to start at 0. Other things, it's better to start at 1. My son learned very early on that since Johnny's a mathematician, if I tell him you can do things 3 more times, start counting at 0. He's old enough now, so it's no longer 2 and no longer 1. For a while, it works. If you start counting at 0, how many terms are there up to AN? Not AN plus 1. How many terms are there up to AN? Up to including AN. How many terms are there in the sequence? N plus 1. So you just have to be a little bit careful. If you're counting at 0 or 1, the number of terms could be a little bit different. Any computer scientists here? So depending on which programming language you're in, sometimes they like to start counting things at 0. Sometimes they like to start counting things at 1. And this can cause a little bit of an issue if you're not sure how to code things. Then we have partial sums. So Sn would be A0 plus A1 all the way up to AN. But in summation notation, it's the sum. It goes from 0 to n of AK. And then the series is S is the limit as n goes to infinity of Sn is just A0 plus A1 plus A2. It's just summing all the terms. And the biggest question is, when does the sum converge? That's what we really want to understand. Sometimes the sum will diverge, sometimes the sum will converge. And so the question becomes, are there easy, simple tests we can use to figure out if it's converging or diverging? So let's try to do low-hanging fruit. Is there anything that we know that must be true about the terms an if we want the sum to converge? So if the limit as n goes to infinity of Sn exists, then what must be true about the individual terms an? They get small. So be more specific when they get smaller. You're on the right track. They have to approach 0. If the individual terms aren't approaching 0, then that means occasionally you're going to get a large boost to your sum. And your sum then can't be approaching a common value. So if you want the infinite sum to converge, the terms have to be getting smaller and smaller and smaller. So this is a necessary condition. And again, what does it mean for a sum to converge? It means that the limit as n goes to infinity of Sn minus 8 equals 0 means Sn converges to 8. So it's very similar to what we did when we had limits of a function. What does it mean for the limit of my function to be f of a as x approaches a? It means as x gets closer and closer and closer to a, f of x gets closer and closer and closer to f of a. So if I believe that it's converging to 8, you give me any tolerance you want. I want to be within 1/10 of 8. Well, okay, fine. As long as n is at least this large, you will always be within 1/10 of 8. And then say, I've changed my mind, I want to be within 1/100th of 8. I said, okay, if you take n to be at least this large, for all n that large or higher, you'll be within 1/100th. And then of course I decide, 1/100 is not enough, I want to be within 1/1,000,000,000. And then in a frustrated tone of voice, I come back and say, fine, take n to be at least this large and you'll be within 1/1,000,000,000. And of course, unsatisfied, and it's, well, actually, I want to be within 1/√. And so whatever tolerance someone gives you, you can always find it in such a, from this point onward, we're at least that close, okay? And you can be a little frustrated when you're talking to them. Now, it can become painful to explicitly write down what is the first n where that happens. You don't care what the first n is, you just get from some point onward, I'm at least this close. So if the individual terms an aren't going to 0, then my sum can't be converging because occasionally, boop, I get a little blip that pushes me on. So this is a necessary condition. There is a huge difference between necessary conditions and a sufficient condition. For a sufficient condition, then that means if that happens, then so does the consequence. A necessary condition says it must be the case that this happens if what you want to hold holds, but it may not be enough by itself. Can somebody give me a necessary condition to pass this class or to win a sporting event? Show up for the fight, or be enrolled in the class, show up to the exam, show up to the game. You're not going to pass if you don't play. Is it sufficient to just show up? No, right? You don't win the game just because you showed up. But if you don't show up, you have no chance of winning the game. So what would be a necessary condition? Well, in most things, it's scoring more points than you allow. And that would be enough to guarantee you winning. So over here, if an goes to 0, does Sn converge? So is it a sufficient condition? Or can you give me a sequence where the terms go to 0, but the sum does not? The sum does not converge. So there's lots of fun sequences. 1, 1/2, 1/2, 1/3, 1/3, 1/3. 1, 4, 1, 4, 1, 4, 1, 4, 1 5th. How many times do I have 1 5th?
5.
5. What comes next? 1 6th, and I have 1 6th 6 times. And so if I look at the sum of the 1/2 gives, the sum of the 1/3 gives, the sum of the 1/4 gives, and so the sum is clearly going to diverge. So the answer is a resounding no. It is not sufficient. So if you know the terms are tending to 0, then there's a chance that it converges. If, however, the terms tend to 0, that is not enough to be guaranteed. And so this is a terrific example of a sequence where the terms tend to 0, but the sum does not converge. All right, so as I remarked, I am sad that I am not able to bring the basketball, hoop. Last semester last year when I taught this, I think it was also after that in the semester. So this is now 2 years in a row when we haven't been able to play a game of hoops. It's a really nice way to illustrate the formula for the geometric series without doing the standard algebra proof. It's a much more memoryless process, which is a wonderful, wonderful idea. It occurs all the time in game theory. We will do instead the standard boring algebra. So geometric series. 1 r squared, r cubed, r to the 4th, and so on and so on and so on. If I multiply every term by 5, I would just change the sum by multiplying by 5. If I multiply every term by 1/3, I just change the sum by multiplying by 1/3. So it's really not a big deal to just assume that it's a pure geometric series, 1 r squared, r cubed. And so what we want to do is we want to study the partial sums. So Sn is 1 plus r squared plus r to the n minus 1 plus r to the n. And the standard way to figure out what the sum is to multiply by r. And if you multiply by r times 1 is, do you write the r underneath the 1? Where should we write it under? Yeah, we're going to basically get a telescoping series. R times r is r squared. R times r to the n minus 1 is r to the n. And then r times r to the n is r to the n plus 1. And we saw this idea of telescoping sums when we did the fundamental theorem of calculus. When we looked at the antiderivative at xk plus 1 minus the antiderivative at xk, and we summed, we just had massive cancellation. So we subtract, and dead. Right? The only things that survive are the first and the last term. So Sn minus r times Sn is just 1 minus r times Sn equals 1 minus r to the n plus 1. So Sn is just 1 minus r to the n plus 1 over 1 minus r. So we can write that as Sn is the sum, k goes from 0 to n of r to the k, is 1 over 1 minus r minus r to the n plus 1 over 1 minus r. So this is the finite geometric series formula. And it's really useful to write it this way, and we'll see why in a moment. We are going to be interested in, well, what happens as n goes to infinity? What will we get? Well, if we want to send n to infinity, what must be true about the individual terms in the sequence if we want to have a hope of convergence? They have to be very careful about less than 1.
Less than 1, but greater than 0.
Well, but we could have things that are negative. So the problem is negative 50 is less than 1, but you don't want to allow negative 50. So what must be true about the individual terms? The individual terms must be tending to, what's my necessary condition? If I want the sum to converge, what must be true about the terms? They have to go to 0. So I need the individual terms to go to 0. So what must be true about R if powers of R are tending to 0? It's not R is less than 1. It's close to R is less than 1. Nope. The absolute value of R is less than 1. Because if R is negative a half, the absolute value is less than 1. The terms will just alternate. That's fine. It's still going to converge. But if R is greater than 1 in absolute value, or in fact, if R equals 1 in absolute value, you'll have trouble. So if R is less than 1 in absolute value, well, as n gets very, very large, 1 over 1 minus R, that doesn't change at all. That's independent of n. And this part over here, because R is less than 1, R to the n plus 1 is going to 0. So if R is less than 1, then S, which is the sum, k goes from 0 to infinity of R to the k, is just 1 over 1 minus R. And so that's the infinite geometric series formula. And it works so long as R is less than 1. Okay. So it's wonderful that we have such a closed form expression. Yeah. If you think back to the integration we've done, most of the time, it's hard to get integrals that have a nice closed form expression. We are lucky that we have one here. So let's test and see if this formula is reasonable. Let's consider 1 plus a half plus a fourth plus an eighth, and so on and so on. So if I draw, here's 0, here's 2. After the first term in the sum, I add 1, so I'm now at 1 unit. I've covered half the distance from 0 to 2. At the next step, I add 1/2, and I cover half the distance. In the next step, I add 1/4, and I cover half the distance. Every time I take a step, I cover half the distance. And so it's quite reasonable that the infinite sum should be 2, because at every moment in time, the next step I add covers half the distance that remains. Anybody know what paradox this is related to? Zeno's paradox, that you can never get anywhere because anytime you move, you can only cover, to get from point A to point B, you first have to get halfway there. And before you can get halfway there, you have to get a quarter of the way there, and so on and so on. The best excuse I ever got from a student for being late to class was, Zeno's paradox was a bitch to them. And just, he just said that calmly and just sat down and just had to accept that as a beautiful excuse. There's a huge difference between the infinite and the finite. At any finite stage, we're not at 2, but in the limit, we will be at 2. All right. What if I do 1 plus 2 plus 4 plus 8 and add the powers of 2? So for this geometric series, what does R equal? So here, this was R equals a half. What is R in this case? 2. And so I get 1 over 1 minus 2, which is -1. So the sum is so large, it exceeds positive infinity, then comes back at negative infinity and loses steam just a little bit before 0. Is anybody buying this? Okay. Why is this wrong? I hope we can all agree that an infinite sum of positive numbers should not be negative. What's wrong? Where's the mistake? I'm sorry? Good. The absolute value of r is greater than 1. So note the absolute value of r is greater than 1. And so because the absolute value of r is greater than 1, can I use the geometric series formula? No. It doesn't matter that the geometric series formula tells me -1. I can't use that. Now, it turns out that there are ways to make sense of divergent series like this. In algebraic number theory, this actually does make sense as -1. In modern string theory and number theory, if you sum all the positive integers, you get -112. And there's a way to make sense of that and to have it reasonable. Okay. So this is a brief introduction to some of the properties of the geometric series. What I want to do now is I will shift to harmonic series. Okay. Very suspenseful as the slides come down. All right. So can the people at home see this? Let's see what this chat says. Yes, excellent. Okay, so the harmonic series is defined as the nth term is just 1 over n. So 1 plus a half plus a third plus a fourth, all the way up to 1 over n is the nth partial sum. So the first few terms, first few aren't too bad to do by hand. When you take the fourth term, you get about 2.08. When you take 100 terms, if you want to do it exactly, you can write out exactly. Well, it's about 5.18. Take the first 10,000 terms, it's 9.78. If you take the first, is that 100,000 or million? No, that's the first million terms. It's about 14. The sum is growing, but it's growing very slowly. So what's the first question we want to ask about the harmonic series? So what should we ask about it? Does it converge? And so we're going to give a couple of proofs that it does not converge, that it diverges. So the first is let's let H be the sum. We're going to show that the sum is infinite. We're going to do a proof by contradiction. So let's assume that the sum is finite. So if the sum is finite, we can have H even be the sum of the even terms, and we can have H odd as be the sum of the odd terms. Which do you think is larger, the sum of the evens or the sum of the odds? Okay, why is the sum of the odds larger? Yeah, 1 beats 1/2, 1/3 beats 1/4, 1/5 beats 1/6, and so on and so on. So each term of the odd beats the corresponding term of the even, so the sum of the odds should be larger than the sum of the evens. Okay, well, I can write my sum as the sum of the evens plus the sum of the odds, but the sum of the odds is greater than the sum of the evens. So if I replace the sum of the odds with another even, I've made the sum smaller. But I claim that the sum of the evens is just half the total sum. Because look at the sum of the evens. It's 1/2 plus a fourth plus a sixth plus an eighth. What can I pull out from each term? I can pull out a 1/2. And so if I do that, I have 1/2 times 1 plus a half plus a third plus a fourth. So the sum of the evens is just 1/2 the total sum. So H even plus H even is twice H even. Well, that makes sense. I have 2 copies of H even. But H even is half of the total sum. And so I now get that the total sum is greater than twice the sum of the evens, which is just twice times 1/2 the total sum. So I get H is greater than H. That's impossible. You can't be greater than yourself. And so what did we assume? We assumed that the sum was finite. And so that assumption must be wrong. Here is another proof that the harmonic sum diverges. So let's look at the numbers, and we're going to play the grouping game. This is inspired by an example we did a little bit earlier. And so what I'm going to do is I'm going to group together sums so that I keep getting a 1/2. And so I'm going to group the 1/3 and the 1/4 together. and I have two terms, each term is at least 1/4. So the contribution from 1/3 plus 1/4 is greater than 1/2. 1/5 plus 1/6 plus 1/7 plus 1/8. I have four terms. Each term is at least 1/8, so the contribution is at least 4/8 or 1/2. 1/9, 1/10, all the way up to 1/16. I have 8 terms, and each term is at least 1/16. So again, I get a contribution of at least 1/2. And so you can keep marching down like this, and you'll see that you can keep adding 1/2, 1/2, 1/2. And this gives you a lower bound. With a little bit of work, you could just do the sums going the other way. Do 1/4 plus 1/5 plus 1/6 plus 1/7. And then that would be greater than 4 times 1/4, that'd be greater than 1. And so you can go in the other direction, you can get upper bounds. With a little bit of work, you can show it's actually growing logarithmically. And that's why it was taking such a long time to see things. Okay, I think that's the last thing I wanted to say about the harmonic series, yes. And so what I will do now is I will go back. Okay. And so the last thing I want to do is I want to do a really good example of why we can't always interchange sums, or equivalently, why we can't always interchange integrals. So we talked a little bit about the Fubini theorem. So for Fubini, the integral over x and integral over y of f is equal to the integral over y integral over x of f if the double integral of the absolute value is finite. And so we had that finiteness condition. We are not proving Fubini's theorem in this class. If anybody is interested, let me know. I'm happy to either talk to you about it or direct you to some resources. What I want to do is I want to give you an example where Fubini's theorem fails. What do I mean by Fubini's theorem fails? I mean, we don't have that the double integral of f is finite, and so the order of integration matters. It's really nice when order doesn't matter. Does anybody remember an order in differentiation where if a condition holds, we don't have to worry about order? We had a nice condition. If something is true, we don't have to worry about how we differentiate. So that was if f is C2, twice continuously differentiable, then the derivative of x with respect to y, so the derivative with respect to x and then with respect to y is the same as the derivative with respect to y and then with respect to x. The order we do it doesn't matter. What I'm going to do now is I'm going to give you an example where the order in which we sum matters. So I'm going to look at an infinite sequence, and in the interest of time, I will only draw finitely many of the dots, but they go off to infinity in the upper right quadrant. And so this would be a 0, 0, a 1, 0, a 2, 0, and so on. This would be a 0, 1, a 1, 1, a 2, 1, and so on. A 0, 2, a 1, 2, a 2, 2, and so on and so on. I'm going to define my sum in the following simple way. And again, while I'm giving you an example where the order of summing matters, I could easily convert this to an area, to a problem where the order of integration matters by smearing these out and having very messy functions. Rather than doing a messy example with integrals to show that the order of integration matters, I would much rather do a clean example with sums to show the order of summation matters. So I'm going to define this to be plus 1 here, minus 1 here, and then 0 for the rest of eternity going on. And over here, it's going to be 0, plus 1, minus 1, and then 0 for all eternity going on. What do you think the next column is going to be? 0, and then what?
0.
And then
1.
And then so on and so on. So let's do vertical then horizontal. So what is each vertical column going to sum to? 0. So if each vertical column sums to 0, what's the sum of 0 infinitely many times? 0. Now let's do horizontal, then vertical. What does the first row sum to? 1. What does the second row sum to? The next row. Every row after the first sums to 0. So if you do the horizontal sum, you have 1 plus 0 plus 0 plus 0. Yep.
Wasn't the last one again?
No, because remember, we only have a finite amount of time today. This should be 0, 0, 0, plus 1, minus 1. I'm only drawing finitely many. This goes off to infinity.
Right, think about that. Where did that 0 and minus 1 or like 1 come from?
This is how I'm defining my sequence. I get to choose what sequence I want to study.
Oh, okay.
So I'm looking at the sum n goes from 0 to infinity, the sum n goes from 0 to infinity of a m n, versus the sum n goes from 0 to infinity, the sum m goes from 0 to infinity of a m n. And we're seeing that the order in which we do the double sum matters. Because again, I'm only drawing a finite subset, but it should be 0, 0, 0, 1, negative 1, 0, 0, 0, 0, 1, negative 1. And that 1 would cancel that minus 1. And so each column is going to have a sum of 0. The first row has a sum of 1, and every other row is going to have a sum of 0. So if I do horizontal and vertical, what do I get? 1. And then 0 does not equal 1. And what goes 1 is if you try to sum the absolute value. Well, I have infinitely many terms that are 1, infinitely many terms that are minus 1. If I do a double sum, that's going to just be, unfortunately, plus infinity. And that's where things break down. So you cannot always switch orders. As a rule, whenever you see an infinity, that is a warning sign that you must be careful. And here, when we have that infinity, we have to be careful. All right, any questions? All right, this is a good place to stop for today. Enjoy the glorious weather.